Now we're going to continue with valence electrons. So we looked at how electrons fill energy levels within an atom. Valence electrons, were really only worried about the electrons on the outermost energy level. And the reason we worry about those electrons is because they're the ones that can actually bond with other atoms. They're not shielded by anything, so they're the ones that actually really determine the properties of the atom. And so when we say properties, what we mean really is sometimes if it's metallic or non-metallic, if it's a gas or a solid at room temperature, but the major one that we mean is how reactive it is. And so there's the octet rule that states atoms are inert. Inert is a fancy way of saying they don't change or they're not reactive when their outer occupied energy level is full. So when their outermost occupied energy level is full, atoms are inert. They will not form bonds. They will not react. They tend to be gases because there's only one atom there, and that atom can vibrate around all over the place. It's not stuck to anything, making it a liquid or a solid. For most atoms, that means 8 valence electrons because that outer energy level is going to be full or stable or completely occupied when it has 8 valence electrons in its layer. There's only one exception to this, and that's helium. Helium is stable with 2 valence electrons because remember, helium only has 2 valence electrons. It's only got 2 electrons total. Helium is the second element on the periodic table, and that's got 2 protons. And then the first energy level only holds 2 electrons, and that's it. So it's stable because that outer energy level is full. So we think of octet to mean 8, and it does in most energy levels. When they have 8 valence electrons, they're stable, they're full, they're inert, but for helium, that's 2. Now, we're going to cheat, and we're not going to worry about all of the inner electrons and protons and neutrons. We're going to use valence dot diagrams that just give us a quick summary of what's going on with an atom. And those are going to use just the symbol of the element and then electrons or dots placed around that symbol to represent valence electrons. We'll get to that example in just a minute. Now, draw the complete electron dot diagram for helium-4, then draw its valence electron diagram, also labeled as inert or reactive. Remember, inert means it's got its outer energy level full. For most things, that's 8. For helium, remember, it's the exception, it's 2. If it doesn't have 8, if it doesn't have a full energy level, it's reactive. So helium-4, we look up helium on the periodic table. It's got 2 protons, 2 P+. Helium-4 means that 4 minus 2 equals 2 neutrons. And then because it's got 2 protons, it also has 2 electrons. So I'm going to go ahead and put that. Protons are 2, neutrons are 2, and then 2 electrons. And that's it. My third electron, if I had one, would go out here on this energy level, which would make it reactive. But because my inner electron is, or my highest occupied energy level is full, this is in fact stable. And by stable, I mean non-reactive. And so I'm just going to say inert. It will not form bonds. It's not going to create new compounds. Draw the complete electron dot diagram for argon-38. Then draw its valence electron diagram. Also label it as stable or unstable. And by stable, I mean is it reactive or not reactive. So stable, not reactive, that's inert. Unstable, that means it will form bonds, it will react. So I look up argon. Argon is the 18th element, so it's got 18 protons. That means it's also got 18 electrons. And the neutrons is given by 38, its mass number, minus 18, that's 20. So in my nucleus, I put protons at 18, I put neutrons at 20, and then I go ahead and I fill in my 2 electrons there, and I need 18 total, so I'm going to put 2, 4, 6, 8. I know I broke my own rule, but I knew that one was full. So 2 and 8 is 10, and then I need 1, 2, 3, 4, 5, 6, 7, 8. And now I'm done, and that's an octet. That's got 8 electrons in it, and so this is, of course, inert. It's not going to react. Now, I forgot to do this on helium. I'll jump back and do that in just a minute. Argon, its valence electron dot diagram, its symbol is Ar, and it's got 8 valence electrons. It's got 8 electrons in its outermost energy level, so I'm going to go ahead and put those in. Okay? And the way I've done that is actually very similar to how I want you to draw electrons on the rings, on the energy levels. No side should get 2 until every side has 1. And we're going to think about argon, the symbol, as being in a box. So when I draw valence electron dot diagrams, and when you draw valence electron dot diagrams, put an imaginary box around your symbol, just like it looks on the periodic table, and then think of each side as a place where electrons can be. And each side can have 2 electrons, but no side is going to hold 2 electrons until every side has 1, because remember, electrons don't like each other. And that's going to help us later when we look at how atoms form bonds. Now, I said I forgot to do this with helium. Whoops. So helium is, of course, got 2 electrons, and so helium with my box, I'm going to go ahead and I'm actually going to pair these 2. Now, I know I just said don't pair any until every side has 1, but the reason I pair those 2 is because they fill the first energy level and they don't form any bonds. And so the empty sides aren't really empty. There's actually no energy level there to hold those electrons. And then let's look at the easy way of doing this. Okay, the valence electrons actually increase as we move across the periodic table. And the periodic table is named periodic because things happen periodically. That means repetitiously on it. They repeat themselves. So the periodic table consists of groups or families, which are the columns. So we say the columns are groups or families, and those run vertically. And then the rows are called periods, and we're going to come back to that in just a minute, and those are the ones that run horizontally. So why are they called this? Well, because a group or family is going to be fairly similar, right? Just like a family shares the same genetics, a family on the periodic table shares similar properties. And so as you look within a column, we're going to see that everything in this column is a very, very reactive metal. And everything in this column is a very inert, non-reactive gas. And the reason for that is their valence electrons. They all have the same valence electron configuration. Their inner electrons vary, their protons vary, but their valence electrons do not. But a period happens this way, and as I move across a period, things change, because first I have 1 proton and 1 electron, then I have 1 proton and 2 protons and 2 electrons, then I start over, and I'm back to having 3 protons and 3 electrons, but that 3rd electron is actually in the next energy level. And so it's 1 valence electron, and then 2 valence electrons, and then 3 valence electrons, and then 4 valence electrons, and then 5 valence electrons, and then 6, and then 7, and then 8. And then we start over on another row, and that repeats itself again because now we've bumped up into the 3rd energy level. And so we have 1 and 2 and 3, and that's why it's called periodic. It's periodic because as we go from one row to the next, we start over on the next energy level, and the valence electrons repeat themselves. They start back over at 1 and work their way back up to 8. And that means, like I said, only the last group is going to have 8 valence electrons. And every other group is going to have a similar number of valence electrons. Now, things start getting a little bit more complex when we get into these middle 10 columns. We will look at those, but for now, don't worry about them. And then this bottom 2 rows, we'll look at those later. We'll see that there's a couple cool things that are how the energy levels actually fill. For now, we're not worried about it. But because the rest of the pattern is increase the valence electrons by 1, and every row starts over with a new valence shell, then as we move across the table, we increase number of valence electrons, which changes our properties, but every column has the same number of valence electrons, which keeps those properties similar. So atoms in the same period have different properties because they have different numbers of valence electrons. Atoms in the same column have similar properties because they have the same number of valence electrons. And you guys can cheat. Right? If all I ask for is the electron or valence electron dot diagram for phosphorus, there's no reason to go and figure out, okay, it's got 2 valence electrons and then 8 valence electrons, or 2 electrons and then 8 and then 1, 2, 3, 4. No, don't do that. It's got, if it's in the first column, it has 1 valence electron. If it's in the second column, it has 2 valence electrons. You skip the middle 10. And you're like, okay, this is 13, but I'm just going to think about it as 3, and then 4, and then 5, and then 6, and then 7, and then 8. And so I can just look at phosphorus, and I can say, oh, well, phosphorus valence electron dot diagram, 1, 2, 3, 4, 5. And it doesn't matter where that one pair goes, go anywhere, but we can see right away that phosphorus has 5 valence electrons because it is in the 5th column. If we cared, we could say those 5 valence electrons are in the 3rd energy level because it's in the 3rd period on the periodic table. Those energy levels have started over 3 times as we add more electrons to it. So draw valence electron diagrams for calcium and bromine and label them as inert or reactive. Well, bromine, if we go find bromine, it's over in the 7th column, and so it's got 1, 2, 3, 4, 5, 6, 7. And I shouldn't have done that. I should have drawn my bromine like this, right? I should have gone 1, 2, 3, 4, 5, 6, 7. But it ended up the same way. No side gets 2 until every side has 1, but it doesn't matter since I knew I was going to get to 7. Calcium, on the other hand, is in the 2nd column, and so calcium has 2 valence electrons.